and you have 1 minute papers for this time. Where did I hide the set list? Here it is. Neil, you're on first.
Right, thanks a lot, Connor. Actually, I'm curious about something before I actually start strumming away. The class test. I'm quite curious as to how you all found it. So can you stick your hands up if you found it, shall we say, comfortable?
Excellent!
And how about if you found it tough, but, you know, not, shall we say, when you want to be stretched, so tough, but you know, the sort of thing you've come to learn. That's good. Oh, come on, you can stick your hands up higher. Yeah. Okay, that's pretty good. And what's the right adjective for the next bit? Who's worried? A few. Okay, so can I just stress, as with all teaching, you know, if you are worried about anything, you have two options. One is to stay silent and worry by yourselves, and the other one is come and talk to us. I strongly recommend the latter. That should have been obvious, but just in case it wasn't, I strongly recommend you don't sit quiet, because your worries will probably not dissipate just by you fretting about them. And that goes for advice in life in general. Right. On we go?
Yeah.
Right. So, in the 1 minute quiz that we just did, there was a fair amount about syntax trees. So I'm going to kick off and talk about syntax trees. So, why do we have syntax trees? That's the first question to ask. Well, I guess, you know, you as people who write programs, and, you know, you're bashing away, typing on the computer, you might type in things like, very simple things like 4 plus 7, and you hit return, and you hope for an answer. And the computer has to go and look at it, and it says, aha, 4 plus 7, oh, well, it's 4, and it's a plus, and it's 7. Aha, I know the answer, it's 11. No problem.
Unless it's PHP, in which case it's 47.
Yes. So, easy. Okay, what happens if I was to say, if instead you typed 3, 3, 6, 4, 9, 1 plus 2? Okay, well, the computer is going to read that. It's going to think, 3. I don't really know what's going on yet. 3, I don't really know what's going on yet. 6, I don't really know what's going on yet. 4, I don't really know what's going on yet. 9, I don't really know what's going on yet. 8, I don't really know what's going on yet. 1, I don't really know what's going on yet. And finally it'll get to a plus sign and think, I'm going to add 2 numbers. Fantastic. But it had to wait a lot. And, you know, when you get large programs doing large amounts of things, you know, you might have to pause, you might have to get through a whole load of the input until you find the really important thing that's going on. So while this kind of thing is a natural thing that you'll write, it is not very good for the computer. It's not what the computer wants. And so one of the arts about good programming languages is to allow you to do, the programmer to do the things that you're good at. And humans are good at, you know, doing various things. High-level thinking, abstractions, understanding stuff, forming mental models, etc., etc. Whereas the computer, what it's really good is bashing away at stuff, which is really dull stuff, but it can bash away and it do it far quicker than you can.
Neil, can you put the pen down when you're gesticulating near the screen? I'm having a nervous moment.
I'm thinking, by the way, of, so just a brief interlude, I'm thinking, by the way, of having some writable walls in the study zones, because that's fun. I saw it in a tech company I visited recently. I think that sounds really cool. So if you think that's a cool idea, let your staff student reps know, and we'll take your opinion on board. But of course, the thing to do is you must distinguish between the writable wall from the non-writable wall. So make sure you're capable of doing that if you think that's a good idea. Anyway, back to the lecture. Where was I? So what we need to do is, this might be good for you, but it's not good for the computer. So what does the computer do? Now, as a person writing programs, you need to know less about what the computer does if you just want to write the program. But this class is about programming languages, definition and implementation. So now you need to know what the computer does, because essentially you're going to write the programming language. So what does the computer really want to know? It really wants to know, not that, it really wants to know, it's a plus. This is a plus. And what is it a plus of? It's a plus of 2 things. 3, 3, 6, 4, 9, 8, 1, and 2. And so these things are called syntax trees. Did I put the pen down or did I keep it in my hand there? I can't remember.
Well, you use the correct end of the pen as a pointer.
I'll just put it down. So, these are what syntax trees are. They're representations of programs and bits of code, but in the format the computer wants. And they're called syntax trees because they look like trees. Now, those of you who wander around the countryside and bits of Kelvin Grove Park and different and are very ecologically aware will may think this is not really like a tree.
It's upside down.
Well,
It's an Australian tree.
yes, the top is often called the root, and these are called the leaves. So it is a little bit upside down, so it's a little bit Australian, but they are kind of like trees. So for example, here's another syntax tree. I might have plus, and then 4, and then minus, 2, and 1. So that's another syntax tree. So you see the idea. They start at the root, which is at the top, because they're Australian, and sort of go down. You get more and more information. So this is 4 plus 2 minus 1. So that's a syntax tree for 4 plus 2 minus 1. Okay, so a large amount of what we're going to do is get you to understand syntax trees, because that's what the computer uses. That's its internal memory or state about what the program it's dealing with is. Okay, so syntax trees, they just basically have a little bit of information, the key information, and then they have branches. These are just always lines pointing downwards. Here there are 2, but you saw in the test you did this morning with the new piece of syntax, you had 3, because new had a variable, an integer expression, and an integer expression. So you can have 3 branches, and we'll see a few of those in a minute. Okay, and then they just keep on growing down. So let's say, I remember that last night at about 2 AM, I wrote this syntax tree. So this is to represent new x is equal to x in x. You don't need to, the computer doesn't need to remember the in part and the colon and the equals. That's kind of taken as read inside this representation. So new just requires 3 inputs to be a proper expression. The variable, the integer expression, and the integer expression. These happen to be integer expressions. Now, that's, I think, all that needs to be said about syntax trees. The only other thing I'm going to say one more thing before I hand over to Connor, is what does the computer do with these syntax trees? Well, the main point about the compilers, interpreters, all these different things is they take programs and they do things to them. So they're going to have to take these syntax trees and do all sorts of different things to them. So for instance, you might in this syntax tree say, oh, I wonder what the value of that is. 2 minus 1 is 1, 4 plus 1 is 5. So the computer might have to turn this somehow into 5. So you could do evaluation, and you'll get 5. Or the computer might want to take this syntax tree, and it might want to think, oh, I wonder what the variables are in there. And you'll find out, well, there's a variable there, so x is a variable. So there's a lot of stuff that we're going to teach you about where the compiler, or the interpreter, or the evaluator, or the reducer, or whatever, is going to take these syntax trees and do things with them. And there's a fundamental principle about how this works. Right, did we bring a huge number of pieces of paper?
Yes, we did. But they're cunningly hidden under the set list.
Ah,
Yes.
so the question is, that's the main question. How does the computer manipulate syntax trees? And it's basically, there are variants and it can become more sophisticated, but basically it's by the following process. 1, manipulate the subtrees, and 2, combine the results into the overall answer. So I'll show you what that means. So let's take a subtree. Let's take one of these expressions. So we had one of these syntax trees. We had, plus 4 minus 2, 1. Now you know what the answer is because you're extraordinarily clever, sharp young people. Computers are, in some sense, they're slow, in some sense they're fast. Maybe especially they're methodical. So what it'll do first, we'll say, this is the first subtree. Maybe subtree 1. And then this is the second subtree. Subtree 2. So what it does is it manipulates, in this example, it evaluates the subtrees. So what happens? Well, we're just working on the subtrees, so that remains a plus. And then it looks at the first subtree, 4. What does it need to do to evaluate 4? Nothing. 4 is already evaluated. So we'll leave that alone. And what about the second subtree? Oh, it's minus 2, 1. So again, it needs to process that. So it'll do the same thing. It'll look at the subtree here, evaluate that. The subtree here, evaluate that. Combine the results into the overall answer and get 1. So when it manipulates this subtree, you'll get 1 there. And then you can see finally, now that the subtrees have been manipulated, we can get to, it can actually work out the answer 4 plus 1, 5. So, this is the general process that we're going to be using in everything we do. We're going to give you some code on your compiler or your interpreter, or when you do reductions or whatever, we're going to look at the subtrees, look at the arguments, work on them, and then finally combine the results we get into the overall answer. So before I hand off, I would like to do an example so everyone check that everyone's with me. So let's write a big one. Oh, let's write something new. That's a plus sign. Okay, so we want to evaluate this. We're going to do exactly what I said before. We're going to evaluate all the subtrees and then combine them to get the answer. So, let's see. How many subtrees are there? 3, yes. So there's the new always has 3 subtrees. So there's the first subtree, there's the second subtree, and there's the third subtree. Okay? So, in the process of this evaluation, what it's going to do is look at the subtrees and try and evaluate them. So, which of these subtrees do you think it would want to evaluate first? Speak up.
X.
Well, it can't really evaluate x because it doesn't know anything about x. You know, you can't make progress on the x. What should I do with x? What should I do with x? What should I do with x? Oh God, I don't know what to do with x. It is just x. It's a good try. I mean, there's only 3, so you try that one. Try that one. You can't make any progress. Only 2 left to go. The middle one. Yeah, this says 5 plus 1. Hooray, we can process that subtree. So, let's process that subtree. That will turn into 6. Okay, I'll do the next step. So now we've got this thing, it says new, x is equal to 6 in this expression. Well, you know, we can't process this subtree because we don't know what x is. We can't do anything with 6 because it is just 6. We can't do anything with x because it's just x. So overall, what we can do is we can say, oh, x is 6. That's the point about evaluating the subtree, so I can put it in here. So now the rule for evaluating the new will say, take the value of x and put it in there. So we'll get this syntax tree. Oops, sorry, that's a 6, 4, and finally 10. Oops. So, that's a slightly larger example. Still very small, but you get the idea. Always evaluate whatever sub-expressions you can. When there's no more sub-expressions to evaluate, if things are working well, then you can actually go ahead and use the rule for doing new and make more progress. Okay, Connor.
Yes. So
add to that, once upon a time in a completely different class, you were taught a thing called proof by induction.
Ah.
And you may be
It's
wondering.
not a galaxy far, far away, is it?
Yeah, and you may be wondering, what on earth was that for?
What's going on here? The step that you make in a proof by induction is that you say, well, if I already have the result for n, I can show the result for n plus 1. So you can say what the step is to process any number. Well, what's going on is just that, if we already know how to manipulate the subtrees, we need to show that we can manipulate the whole thing. So it's the same idea of processing whole things by processing their pieces and then combining the results, where for a number, numbers are just made by 0 and adding 1. So sort of 1 plus is how you make the next layer of structure in a number. So the actual concept of doing structural induction on trees is actually genuinely useful. It's how stuff works. And it's sometimes a bit of a shame that we teach you induction as if it's about numbers. It's about big things made of smaller things. And the way you process them is process the components and then finish the job by combining the results. That's all that's going on with induction. Okay, what am I supposed to be talking about? I'm supposed to be talking about grammars. Maybe, I'll do this with a piece of paper. Let's see. Neil's going to be red and black, I can tell, because he's an anarchist. And I'm going to be green, because I'm Irish. Right, so how do we write grammars down? We might write, for example, a grammar of Boolean expressions. It might look like this. We might say 0 is a Boolean expression, 1 is a Boolean expression, and I'm going to write an ampersand today. We might write that sort of thing. So this is hopefully reasonably familiar if you did CS311. So how does the grammar work? Well, first of all, there are two sorts of symbol. Well, no, there are three sorts of symbol in this picture, right? There's this colon, colon equals and these vertical bars, and they are part of the syntax of grammars. They say Boolean expressions are defined to be made by one of these three possibilities. And then in each line is called a production. You say what different ways you have to make a Boolean expression, and in each production you have two kinds of symbol. You have terminal symbols. They're called terminal because that's where you finish up, and also because you can type them in a terminal. They are the things that you actually type in your source code, like the 0, the 1, and the ampersand. And then these things that are enclosed in the angle brackets are called non-terminal symbols. They stand for the types of things that we're building. So here, a grammar says, it takes one of the non-terminal symbols and it defines the different ways to make things of that variety. So we're saying, there are such things as bexps, and here are the ways to make them. You've got a choice of three things. Okay, is this vaguely familiar? So what we're saying is a Boolean expression is either 0 or it's 1, or it's a Boolean expression then an ampersand then another Boolean expression. So what is that telling us? It's telling us, we might write down a whole bunch of grammars for different sorts of thing in general. So it tells us what sorts of thing exist. And it tells us the different ways to make them. So that's to say, we now know what the possible syntax trees are for Boolean expressions. We've got a little Lego kit of syntax trees for Boolean expressions. We know that there's I'll draw them in boxes. There's a piece that goes like that, and there's a piece that goes like that, and there is another piece with an ampersand in for a label with two legs to attach other pieces to. So what we're really saying is, here is the Lego kit from which you build syntax trees for BEXPs. Okay? And you can see why does this thing have two legs? Because it has two substructures represented, given by non-terminal symbols. That's to say, two other things are going to plug in for this non-terminal symbol and this non-terminal symbol. So we get two pieces of information at once. We've seen one of them. That's to say, which kinds of things exist and how they're put together by the different productions. Right? Crucially, you know that whenever you have a Boolean expression and it's a legitimate one, it must have been made by one of the productions. Right. But the other thing that we've written down in the same act of writing this grammar is that we've said what a programmer has to type in so that the compiler can generate a syntax tree for a Boolean expression. So we've explained simultaneously the abstract structure behind the scenes of these syntax tree and the concrete way programmers should be typing in Boolean expressions. For example, this tells you that it's perfectly okay to type, I don't know, 0 and 1, and that ought to turn into that lump of Lego. So it's a 2-for-1 deal with grammars. You're on the one hand specifying what it looks like to the programmer, and on the other hand, you're explaining what it looks like to the various processes that manipulate programs. So that's why it's a kind of neat notation. Okay, so I should say something. I should possibly even switch to using a computer for this bit, if I can persuade. Sometimes machines don't recognize my corporeality. Right, what do I actually want? I actually want to click, I've put the link to the GitLab repository for the massive machine on this page, in case anyone's interested in what's going on behind the machine, behind the scenes. We'll end up getting there. It's all implemented in Haskell. In this class, I won't expect you to program in Haskell, but we'll need to install software that I've written in Haskell. Let me make the font a bit bigger. So you can see, okay, the thing at the top of that file is not a grammar, but then a whole bunch of other stuff. Those things are grammars. So let me say, so the syntax that we write for grammars is exactly what I was just doing by hand on the document camera with non-terminal symbol, colon, colon equals, vertical bars separating the productions. So in this language, the only thing that matters, this is just me being tidy. this layout. You don't have to put them all on different lines. You do have to separate them by vertical bars. And the other thing you have to make sure you do is if you spill onto more than one line, you have to make sure the continuation lines are indented with at least one space. So that's why these are shifted in a little bit. Okay, that's one thing. What else do you need to know? There's a traditional response from systems administrators to users who don't read the instructions, which is RTFM. Yeah, well, I recognize I have an obligation to WTFM, but you know, I can hardly respond RTFM if I haven't WTFM. That's yeah. If you're, that's to say, I need to write some notes about how this, what the instructions are. What are the other things to say at this stage? So we'll be getting you to write grammars in this language and then crunch code with them. So you will need to grapple with this. In this language of grammars, we insist that you use brackets in a balanced way. The concept of brackets is built into the language. So if you're using brackets around a square or curly, then they need to be balanced, like they are here around block or around this Boolean expression in the while. The other thing we give you for free is that every grammar is automatically extended with round brackets for resolving ambiguity. So if I switch back to document camera, at the moment, if you were to type in 0 and 1 and 1, then the trouble with that is that it's grammatically correct, but in, sadly, more than one way. Can you all see that there are two syntax trees this could possibly be, depending on whether you put this ampersand at the top or this one. And if it was even longer, with more ampersands, there would be even more possible combinations. So there are various things that one does about that. I'm stealing your stuff. I just wanted to say that as a user, you can always write parentheses round a sub-expression to make it clear what the structure of the syntax tree is. Now we know this one's at the top and this one's underneath it. So the point only for our language of grammars is that you don't need to write anything to say, oh, and by the way, you can always put parentheses in to resolve ambiguity. The system gives you that for free. There's one other entertaining gotcha in the syntax of grammars, and that is, what if you want to use a vertical bar as a piece of syntax in your programming language? If I just write a vertical bar here for or, I was very careful not to write or in my Boolean expressions. You may have been suspicious. If I just write a vertical bar here, then it looks like I've written down two productions. And that will really mess things up. So the rule is that when you see a backslash in the middle of a terminal symbol, it means the character that's after the backslash. So this is a way of saying, this is the terminal symbol vertical bar, not the vertical bar that separates productions. And the only exception to that rule is if there's a backslash all on its lonesome. That just means a backslash. Okay, so that's our language of grammars, and that's how we tell the computer which things exist, the different ways of building them, so correspondingly what the syntax trees are going to be like as far as the computer is concerned, and what the code is going to be like as far as the programmer is concerned. 2-for-1 deal, all by writing down a hopefully sensible grammar. And then the business of figuring out how to do stuff with these programs is exactly what Neil talked about in the last segment. Just, you process the whole thing by processing the pieces. Okay, I've said it. I've queued you up the IMP grammar without explaining. I've explained the grammar of the grammar, but not the grammar.
Thanks, Connor. Always a pleasure. I was wondering if I could just sit and watch for the whole time. Seems there's more work for me to do. Right, so just to remind us, we need to know what are programs. What is the syntax of our programming language that we're going to implement? And grammars are what is the mechanism we use to define them. Now, you might look at them and you might think, oh, well, it's kind of a bit long. I mean, I'll try not to break your computer, Connor. So let's say we start there. So now, actually, the grammars, let's start. Let's start from here. The first bit tells you, this is the grammar of an argument. An argument is...
Argument list. Yes.
Huh?
So the grammar of an argument list. Yes.
Well, indeed.
Yeah.
It's either nothing, that's fine, there are no arguments. If you look carefully, you'll see there is nothing there. It's not like there's nothing there is nothing there. So you can have no arguments. Or you can have an integer expression followed by some more of these things. What are these things? Well, there's nothing there. Or there's a comma followed by an integer expression followed by some more of these things. So that's part of the grammar. But it goes on. It's quite long. So what are these integer expressions? We've got to tell you. Well, an integer expression, as Connor alluded to, is one of 1, 2, 3, 4, 5, 6 things. There are 6 ways of making integer expressions. You could either just write a number, or you could just write a variable. Or you could write an integer expression and then write one of these IOP things, and then write an integer expression. Oh, I wonder what an IOP thing is. Well, it's down here. An IOP thing is it's either the symbol plus or it's a symbol minus. That explains this. So another way to write an integer expression is to write new. And then you have to write a variable, then you have to write colon, then you have to write equals, then you have to write another integer expression, then you have to write in, then you have to write another integer expression. Or you have to write the word do, and then you have to write a command. Oh, what's a command? I haven't told you. So let's go down here. So what is a command? Well, you have to write a curly bracket. This curly bracket, it's a short symbol, but it's just like new and do. You have to write it. You have to write this curly bracket. And then you have to write a block. Oh, what's a block? Oh, it's fallen off the edge of the page. Block isn't too long. A block is either nothing, or you have to write a command, which I'm busily explaining to you, and then you have to write a semicolon and then another block. So you carry on like this, and then you have to eventually put the curly brackets. Or to write a command, you have to write a variable, and then a colon, and equals, and then you have to write an integer expression, etc., etc. I won't finish off. So there's one thing to note. It is long. And you might think, oh, there's a lot for me to remember there. But as with everything, the reason we tell you this stuff is it makes your life easier. I'm fond of reminding students at this stage in various stages of the courses. You might think, God, that's a lot of work to do. I think it might be an easier way to do it. But you'll find any other way is more complicated. We're not here to introduce pain. We are actually angels of mercy. We are making your life easier. So, at a moment, you might have to have a little bit of trust that this is making your life easier, but it is. And the reason it's making your life easier, the reason any other way is more painful, is this is precise. This is absolutely, completely, 100% precise. You see, humans, we can deal with a bit of ambiguity, a bit of waffle, a bit of uncertainty. We can use our intuition, we can use our hunches, we can make guesses, we can do all of those things. Computers can't. They insist on absolute total precision, because they can't stop and say, oh, Connor, what's going on here, like I do when I'm preparing this stuff. So, it is longer, but that is because it's precise, and you often get this trade-off. You can have precision, but the price is length. Or you can have imprecision and brevity. Now, we often have conventions, so that'll try to make it smaller, but this is the point about doing it this way is to give you that precision. So, what you need to do, so this is the test for you to understand how I understood this part of the lecture, is say, do I understand this grammar? It is slightly longer, but it's the same principles for that bit of Boolean expressions that Connor was talking about, and the little grammars that we gave you in the quizzes, in I think questions 0 to 4, and then later on in questions 10 to 14. They're all grammar. So if you did those parts okay, then you're flying. If you found those questions in the quiz difficult, then that shows that you're ready to learn. You're in a great position, you're ready to learn. And you have learned if you can look at this and say, I'm not scared, it's long, but it's actually obvious. It tells you all that you need to know. Again, an integer expression, I just write a number, I just write a variable, I write an integer expression, then put plus minus, then put an integer expression. Right, I should give Connor some time now, I think.
Yeah, we're quite low on time. We're only halfway down the page, but let's see what
You've done a bit of the latter parts.
Yeah, it's true. Yeah, I was going to say, just while they're on the screen, life is subtle. This is the grammar for a list of integer expressions that has commas in between them, right? So if there's only one integer expression in the sequence, there's no comma at all. Yeah? You got something that looks like E1 semicolon, or E1 comma E2 comma E3, right? 3 expressions, 2 commas.
We can see it.
Connor?
So yeah, that's a good point. Thank you for that. Yeah, 3 things, 2 commas. If you have one thing, then there's no comma, and if there are no things, it's just completely blank. So that means there's a sort of slight difference between how you deal with one thing and how you deal with more things. And what that grammar was telling you is that a list of arguments is either empty or it's one expression followed by a bunch of comma expressions. Whereas the grammar for a block tells you that every command must be terminated by a semicolon. Jumping around all over the place, come on. Yeah, so that means a block looks like command 1, semicolon, command 2, semicolon, command 3, semicolon, with an extra semicolon at the end.
So, Colin, can I just pause for a second? So, test for you. Ask yourself, do I understand why the grammar for blocks gives things like this, which end in a semicolon, which must end in a semicolon, and the previous grammar gave you things like this, which didn't. If you understand why that's the case, you've understood this bit of this lecture.
Right. So, I'll just show you I'll show you another grammar, which is
If there was a whole school dedicated to this kind
the
of
grammar
stuff,
of lambda terms that we type in. Of course, I need to do that. And yes, so we've thrown in a bit of arithmetic for as well as the regular lambda terms. You can take that or leave it, but we're saying, oh, excellent, cheers. We're saying that a term is either a variable or an application of one term to another, or a backslash, which is the closest we can get in ASCII to a lambda, and then a variable, that's the name of the input, and then an arrow, because that's more visible than a dot, and a term that says how to compute the output. And one thing you'll notice with this grammar is that it doesn't tell you, he says back on the document camera, if I write FAB, there are far too many syntax trees for what that might be. Yeah? That might be, well, there's certainly two. That might mean f of a, b, and f of a, b. And it gets even worse with things like f lambda x arrow st, where you don't know, you know that at least the s must be in the body of the lambda, but maybe the t is as well, and stuff like that. So the grammar alone there hasn't explained the conventions for grouping, right? We so far haven't done anything that corresponds to the things like the BODMAS rules you learned at school about how if you have like plus and times, it's always, the plus is always on the outside and the times is always on the inside. So this language of grammar so far does not allow you to explain that, yeah. Do you know which of these two, this one, the FAB ought to be? By any chance? The top one. That's to say, as Roger Hindley used to say, application associates to the left, rather as we all did in the 60s. So it's we need a way to tell the system that we mean this one, not that one, or we're going to get into trouble, which means I'll have to implement that. It'll turn up. Okay. So yeah, so ambiguity is a problem. Parenthesis is one way of resolving it, or having some way of saying these are the conventions for resolving ambiguity. That's what operator precedence and things like that are for. So we'll sort that out. Another thing you have to watch out for is if I write something like lambda f arrow lambda x arrow, and then I write fx with no space in between. We have just snatched defeat from the jaws of victory, because this is the variable f, this is the variable x. How do we, if we wanted this to be the application of f to x, we needed to put a space in there. So that's to say, what we're missing from the grammar is how to cut up the text into the chunks that are going to get turned into the syntax tree. And the system will certainly treat fx with no space in between as one chunk rather than two. So that's to say, the grammars don't work on raw characters. They work on chunks of characters called tokens, or lexical tokens they're called. So there's a process that happens before the grammar kicks in to take your input and chop it up into tokens. And yeah, so that's, so I'll write, so there are precise rules for what constitutes a token in this language that I will write down rather than blethering on about them. But that's the phase. You start off with something that's just a string. You turn it into tokens. That's a process called lexing. And then you take the resulting sequence of tokens and throw your grammar at it. That's called parsing. And you end up with a syntax tree. So that's the first thing that happens when your text file arrives at an implementation of a programming language. Lexing, parsing, and then you get the syntax tree, and then the computer can go to work. There's an old programming language wars are rife on the internet, and programming language design committees have them worse than the internet. So there's an old adage from Professor Phil Wadler in Edinburgh. Wadler's Law, it's called. It's people spend 10 times as long arguing about what the syntax of a programming language to be compared to the semantics, right? Nobody cares what it does, right? They spend 10 times as long arguing about what it should look like. And then they spend 10 times as long again arguing about the lexical structure. That's to say, which things ought to be separate tokens, never mind what the syntax trees ought to be like. And then they spend 10 times as long again arguing what the lexical structure of comments ought to be like. You know, do comments begin with a pair of slashes or a pair of minuses or what? The most violent arguments are had about the most trivial things. And somehow, you know, what the program ought to do in the end doesn't get a look in. Sad, but true. Anyway, what we're talking about next time. I wish I could remember. I think my phone knows, but I don't. Hopefully next week we'll get your first assignment to you once I've finished building the kit. One piece of administrivia, we realized that we weren't going to get the first exercise out to you in time for a week 3 hand-in, so we've pushed that back to week 4. So exercises due weeks 4, 6, 8, 11. Okay, but we'll get cracking starting next week. Okay, thanks folks. Have a great weekend.